Hello everyone. We are looking at question 49 of the 2015 chemical engineering paper from the subject of heat transfer. The question is, a heated copper sphere of surface area A and volume V is immersed in a large body of cold fluid. Assume the resistance to heat transfer inside the sphere to be negligible and the heat transfer coefficient H, density ρ, heat capacity C and thermal conductivity K to be constant. Then at time t, the temperature difference between the sphere and fluid is proportional to this. So here, basically, we have been asked to derive the formula for the lumped heat capacity in our case. So that is the temperature will be a function of time, and we have to derive what is that correlation. Okay, so let's just consider a vessel in which we have this cold fluid, and we have immersed the solid copper sphere. If the Let's consider the temperature at any given time with T in this case, and at time T equal to 0, the temperature will be T naught and the temperature of the fluid will be T infinity. And here we have been given the resistance to heat transfer inside the sphere is negligible. So that is resistance to Q inside sphere is negligible. So we can write the heat balance across this system, and it will be equal to mass, where m is the mass of the fluid available, then Cp, no, m is not the mass of the fluid, m is the mass of the sphere available, Cp, then this temperature, how this temperature of the sphere varies with time, that is dt by dt, and it will be equal to Ha delta T, where delta T will be T infinity minus the temperature of sphere, that is T. Now we need to integrate this equation to find temperature as a function of time. So we can write this as dt upon T infinity minus T is equal to Ha upon mCp into dt. Here in the given question we have been given that the H, rho, C and K, everything is constant. So basically this term will be constant. Now we can integrate this equation, let's say from T naught to T. Similarly at T naught time was 0 and here it is T. So if we integrate this will become minus of ln of T infinity minus T upon T infinity minus T naught is equal to Ha upon mCp into T. That is T infinity minus T upon T infinity minus T naught is equal to exponential of minus of Ha mCp into T. Now in the given question we have been asked in terms of rho and V, so that is we will replace this mass by rho into V. Now this equation we can also write it as T infinity minus T naught is equal to T infinity minus T naught into exponential of minus of HAT upon rho VCP. That is the temperature difference between the sphere and the fluid. Here it is T. That is the temperature difference between the sphere and the fluid is proportional to this term exponential of minus HAT upon rho Cp. So from the given option, we can see that option A is correct, that is temperature difference will be proportional to exponential of minus of HAT upon rho Vc. That is, we will select option A as the correct answer.